G'day, I'm Ray Tomes from Aotearoa, also known as New Zealand. Today I'm going to talk about harmonics theory, but from a very different perspective than I've done many talks before. Richard did an 8 video series which are available on the Cycles website. This one is going to start not from what's happened in cycles and working towards the underlying things, but it's going to start from the underlying physics and show why the harmonics theory must come about. So I'm going to start with physics, and the time to start is the 19th century. A lot of the physics was being discovered to do with electricity and magnetism at that time, and this culminated in James Clerk Maxwell developing his famous equations called Maxwell's equations, which explain why there are electric waves and magnetic waves, and that the two combined actually produce electromagnetic waves, which is what we call light, and also all the other things in the electromagnetic spectrum. And he worked out at that stage what the speed should be, and it turned out to be correct. That was the speed of light. So at this point, modern physics really got going in terms of how the universe worked. There were a lot of great guys in the 1800s doing this work. And after it, there was a realization by one person who worked out that if there are standing waves of electromagnetism, there must be possible to be standing waves, and that these would probably be what we call atomic particles, which we hadn't even discovered at that point, but there would be such things. And so unfortunately, he died in his 20s before he could say much more about it. So what happened next is they understood that these waves could be explained by the motion of waves through a tensile medium, which was called the ether. I like to spell it A-E-T-H-E-R, but you can spell it another way if you want. And the ether was very popular at that stage as explaining these as what was going on. And basically, I describe it as being like a bowl of what we call jelly and what Americans call jello. And you give it a bit of a wobble or a bang and a push, and it bounces backwards and forwards, and waves travel outwards all over the place. Except that in the case of you can also do it with a big hunk of steel, like the man in the Rank Xerox film, bong, and or was it brass? And that will have vibrations as well, but much faster ones. We can observe them in the jelly. The waves in electromagnetism are vastly faster still. They travel 299,792,458 meters per second. So that's a long way. It takes 8 minutes to get from the sun to the earth at that speed. So this is going on, and they understood that these would work if it was waves in an ether. So then some people called Michelson and Morley decided to see if they could detect the motion of the earth through the ether, because then that would be rather interesting. And they set up an experiment and they tried to measure it, and the results showed it wasn't moving as fast as it should have been. They got a result which was near enough to zero, but not quite, a little more than zero, and there's been various discussions about that since. But at any rate, it showed clearly we were not moving at the velocity of the Earth around the Sun through the ether. And in fact, there should have been a lot of other velocities around the galaxy and all these other things as well. So that confused a lot of people. It didn't stop the likes of Einstein, Michelson, Morley himself, at least one of them, and a lot of other famous physicists, Dirac, Lorentz, all continued to believe in the idea of an ether. But the problem was, if the ether was this very high tensile medium that waves could travel through, how did the Earth travel through it without resistance? There's no resistance. The Earth goes around the sun over and over. It doesn't come to a screaming halt. And the reason that they got that wrong is they assumed that it was like a knife going through a block of butter, and it would meet resistance. But they had the wrong idea, because matter is standing waves of the ether, and therefore they move through the ether the same way that electromagnetic waves do, because that's what they are. So that wrong assumption confused them for a long time, but eventually, later on, de Broglie showed that in fact matter is made of waves, and that's still, the lesson's still not been properly learned, and there's been some more of that. So Einstein did his equations. Einstein never felt that the Michelson-Morley experiment showed what other people thought it showed. He always thought it would be a null result, even though he thought there was an ether and so on. So maybe he had a feeling that those were the waves. But later on, he got confused, because when they did some experiments, it showed that light seemed to be particles, not just an electromagnetic wave. Now, it didn't actually show light was particles. It showed that light was emitted and absorbed in discrete amounts, depending on the frequency. And that equation, E equals H times frequency, is called Planck's equation. Planck's constant is the constant in that. And so that was where it rested for a while, until de Broglie came along and showed that with these equations, and they had shown that light going through two slits made an interference pattern. So it was quite clearly waves to do that. But at the same time, they had shown it was particles, because it got absorbed in discrete amounts. I want to say there's no contradiction between those. Light does not have two natures. It has one nature. It's a wave, and it gets absorbed in discrete amounts because of the wave structure of atoms and electrons going around the atom. They move orbitals, and they are discrete orbitals, so there's a discrete amount of energy absorbed or emitted when they change orbitals. So there's actually no contradiction there, and all of the mysteries, there's a lot of other mysteries we'll go through that are in physics, and they all, people say, if you think you've understood physics, you haven't, because it's too weird. It's not weird. They've just thought about it wrong. And so I'm going to say, yes, all the physicists got some things wrong. They all got it wrong that light travels as particles. It doesn't. Even the most famous physicists have said that. Light travels as waves. It gets absorbed and emitted in discrete amounts, which is, in modern physics, it's often taught that that Schrodinger's equation, which describes what happens in quantum mechanics, is a function that allows you to calculate probabilities. Well, it does do that, but Schrodinger himself thought that it was a real wave, that what really happened, and it can be seen as quite similar to electromagnetic waves, but it's got a little bit more information in it. I think there's someone's proved you can map them onto each other. So Schrodinger's equation gives you these waves, and you can calculate probabilities, but it shows that a wave goes out at the speed of light from any event, quantum event, and the same as it arrives whenever there's a quantum event. Some wave arrives there and does that. Now, I want to give you a parallel to say why that people are wrong that say light is made of quanta, particles traveling. Now, even the great even Feynman said light is made of particles. I'm going to say Feynman was wrong when he said that. Feynman was a clever chap, and he got a lot of things right, but he got this one wrong. I'll give you a parallel example. Let's suppose we have a bucket full of water and a tap dripping into it. Blip, blip, blip. What happens is waves go out from the point where that hits. They spread out over the surface of the bucket of water, and sometimes a drip falls out over the edge. Now, it's got to do that because the bucket's full, and if we put 1,000 drips in, about 1,000 are going to come out, very close to that. So we've got conservation of energy. And what actually happens, the drip that goes out, when it hits the sides of the bucket at various places, it will bounce off. So there's old waves getting weaker and weaker, bouncing around the bucket everywhere. And so when a new drip comes and it makes a wave coming towards the edge, when it gets there, if a couple of old waves happen to intersect with it at the time, there will be enough energy to cause a drip to fall over the side. Now, the drip falling in is an emission event in quantum mechanics. This is a parallel. The drip falling over the side is an absorption event. The wave travelling out is the wave function, and it does travel at the speed of the wave in the medium, which in this case is the water, but we're thinking of that as the speed of light. Now, the drip that fell in and the drip fell out are not the same one. There is no such thing. And there is no such thing as the collapse of the wave function in the real sense. What happens really is that the waves combine enough to cause a drip to fall out. Any one drip in might cause two drips to fall out, or none. It's a, what do you call that function that has an average of 1? I'm getting old and silly and can't remember things. There's a function which has an average of 1. It's sometimes 0, sometimes 1, sometimes 2, 3, 4, but much less likely so. So that's what's happening. The equivalent thing is happening in the universe with quantum mechanics. The collapse of the wave function is a wrong concept. There's a very good encyclopedia called the McGraw-Hill Encyclopedia of Science and Technology. And it's got many volumes, and probably more than one volume in total on quantum mechanics, but it's spread around in multiple different volumes. If you look up in the index for collapse of the wave function, it's not there. It doesn't exist. That's because the very best physicists know that there's no such thing. They don't waste their time arguing with the other ones that go on about it, and it's taught as if there is such a thing and that this is meaningful. So a lot of physics is based on stuff which is not good physics. People have even said, if you think you understand it, you're wrong, because it's impossible to understand. It's extremely mysterious and weird. I'm going to argue that it's not. It's what people are doing with their minds that's extremely mysterious and weird. That the physics is actually very straightforward once you eliminate the mistakes people have made over the years. When the waves are sent to the two-split experiment, waves go through, and the light and waves, and they make an interference pattern on the wall behind. This is well known and proves quite clearly that light is made of waves. However, the particle nature of it is that there's one wave, comes through, another one comes through, and so on when they're emitted, but usually they're so fast you can't detect them individually. So you get this interference build up. They've tried to do experiments to see, does it go through one slit or both slits? So they put a detector in one slit. Now, when you put a detector in one slit, or even in both, it only goes through one. Why is that? Because there are so many waves going out, and the probability of detecting one is extremely small because the wave spreads all over the place. And the detection chance is very small. It's like the drip over the side of the bucket. They don't go. It doesn't fall over everywhere. So what happens is you get a detection of one. There's only one chance in a million you'll get a detection on the other one at the same time, because the waves spread out and it just happened to have the right combination of background energy to cause the detection there. The same as what I was describing with the water. If you do get one in a million that's there, you would just call that one a coincidence. It doesn't matter. So they're looking at it the wrong way. They're misunderstanding what's going on with the light spreading out and with the events that happen. So Schrödinger considered his equation to be real waves. And I think he's right about that. They're real waves. They're the same thing as electromagnetic waves. His one is just a better way of expressing it all that combines it all in one equation instead of needing lots of equations like in Maxwell's equations. Incidentally, what we call Maxwell's equations, it's not Maxwell's equations. Who was it? I think it was, not sure who it was, might have been Hephaestus. Somebody took his and rearranged them in the modern form. His were actually in a different form to start with. So it's gone through a few transformations. There's one other experiment that I'd like to mention. It's sometimes called the aspect experiment because Aspect was one of the guys that did it first. It's also called the EPR, which is Einstein, Podolsky, Rosen. I've got one of those names pronounced wrong, because they tried to show that that something about quantum mechanics was wrong. In actual fact, they were wrong. The quantum mechanics was right, but there's a better way of looking at it. The thing is, if you have a quantum of light, if there's certain chemical reactions where bang, it'll send off light in two directions, because the atom actually goes boom and sends off two. Now they will be polarized the same way. So if you put polarizers there, You can put a polarizer in, you can turn it, and a polarizer, you know, with like your Polaroid glasses, only lets light through when it's polarized a certain way. So the glasses generally will let it in through when it's that way, but not this way, because light that reflects off water or off snow is polarized that way, and it puts glare in your eyes. So when you do the polarizer, you only get it the one way. Now, when you have two polarizers detecting this event at the same time, then they will actually be polarized the same way. Now, you don't know which way they're polarized, but what they do is they start off with the two things lined up exactly the same, and they do the experiment. And that when one detects, the other one probably detects also. Then they gradually rotate one a little bit, and they do this through all the different angles until it's at right angles. Once you go after that, it's equivalent to going the other way. So that when they do this, they have stated that classical mechanics predicts a cosine wave. Now, that's not true. We'll come back to that. But quantum mechanics predicts a cosine squared wave. Now, what that means is that that you get very few events where they are at right angles to each other. Now, whereas you get many events where they're lined up the same way. Now, they're correct about the classical one in one sense. If the wave is that way, if the wave is like that and you tip at some angle, then the cosine of that angle is the probability of a detection. But that's only if you know it's lined up with that one, but you don't. You've got two, and you're doing detections of both of them. So when you do that, you have to actually consider that the photon might be at any angle. You don't know its angle, and you've got to do the detection. What's the probability of getting a detection at both? And the answer is, if you integrate it over all possible angles, and I've done this, the result is cos squared. Now, I've checked this with a physicist, and he says, yes, your calculations are correct. That is what happens, and that's the right result. So classical physics actually gives the correct result for polarizers in this situation. Now, this experiment has been misinterpreted. They've got the wrong result because they've assumed classical physics is wrong when it's right. And what they've done is they've then said that if you let those two things go a long way away before you do a detect, that what you do, then when you detect one, it affects the detection on the other. It doesn't in the slightest. They just do what they were going to do always. They call this quantum entanglement. They say that what you do at one place affects what's happened at the other place. If that was true, you could send information faster than light. They say it happens instantaneously. You cannot send information faster than light. No one's ever done that successfully, and the best physicists agree you can't do that, which means the best physicists are agreeing that this entanglement thing is total nonsense. There is no such thing. They're entangled, yes. The two of them have got the same angle of that they're polarized, or whatever other property they're measuring, but that's all. So there's nothing mysterious happening. There's no flash thing going across the universe at instantaneously. So where does this leave us? It means that there are whole books and articles written about quantum entanglement and this other stuff. They're all nonsense. They're all total nonsense. It's like how many angels can you have dancing on the head of a pin? This was a popular thing at one stage. Now it's all about quantum entanglement and how you can do stuff with that, which you can't. It's angels dancing on the head of a pin. Let me make that very clear. It's nonsense. Now, I mentioned de Broglie and how he showed that that particles can also interfere, his equations show that there are multiple different waves associated with a particle. You can get this result. A colleague, Gabriel Lefrenier, who died a few years ago, and he was in Canada, French-speaking Canada, he made some very nice diagrams of all these, of how these waves look. And you can actually see the different speed waves that he says exist, that de Broglie said exist. Interesting that a man that speaks French carried on from the other man that speaks French. So that was their contribution. And so de Broglie showed that there's a wave nature to all particles, and this is when they started to get into this wave-particle duality. Again, it's unclear thinking that's caused this. All particles are waves. That's all they are, a spherical standing wave. Energy, the wave is coming in, goes through the middle, and comes back out again. Now, at one stage, I realized this from my work on harmonics theory. I realized that there's a sequence of things: the Hubble scale, the scale of galaxies, the scale of stars, planets, moons, a couple that we don't see, cells, atoms, nucleons, and then you can predict quarks from that as well, or quarks if you're an American. So that whole structure led me to believe that that particles were standing waves, because I had established that there were standing waves on the larger scale already. So believing they were standard waves, I put a little article on the internet. This is early 1990s. And I said, I think that particles are standing waves of electromagnetism. And mostly it just got ignored. I got called a silly fellow by some physicists. But I got an email from a fellow named Milo Wolf. He said, welcome to the club. I said, what club's that? He said, the club of people that understand that particles are standing waves. I said, how many are in the club? He said, 2 now. So that was quite funny. But in actual fact, there had been a couple of people before me, and I think before him as well, that had this understanding. He tracked them down. One of them was the fellow who died too young after Maxwell. His name won't come to me at the moment, but it's there in Milo's book. Milo Wolf has written several books which he explains all this. He has published papers that show an electron is explained totally by a standing wave of electromagnetism. Every property of the electron comes out of it, including the spin half. It's quite amazing what he's done there. So he's a physicist. He was a physicist in the university, but he's not recognised for the important role that he's played in physics, because so many people are still going down the wrong path and they don't want to cross over to his right path. But some of us others have, and since I joined the club, there's been many others join that club. So there's a lot of people. You'll find them if you look up wave structure of matter, or WSM. You'll find a lot of people talking about that understand that matter is made of waves. De Broglie proved it, in fact. Once we understand that the universe is pervaded by a medium, which I call the ether, which is it's not popular to call it the ether these days. People call it the 0-point field, the this, the that, the other, or the electromagnetic field, and all sorts of stuff. But it's what used to be called the ether, and I don't think there was anything wrong with that word, so I still use it. I understand ether as being like you get a bowl of jelly, that's Jello for Americans, and you give it a wobble, and waves whip around it everywhere. And the way it behaves is according to the wave equation. Waves equations pop up everywhere in physics, and they are the equation for the universe. Now, once you understand that, you understand that there can be very large waves, there can be medium waves, small waves, they're spread all over the place. And the largest wave will be the universal wave, the wave that oscillates once per cycle of the universe. And the cycle of the universe is much longer than the age of the universe, according to the Big Bang Theory. Now, I've said there need to be some corrections in particle physics, and I'm going to give you some in general relativity too, in the understanding of it. The equations of general relativity are correct, and most of the equations of quantum mechanics are correct. It's the interpretations that are wrong, and they lead people down wrong paths. So let's say we have a wave that's the size of the universe. It's oscillating away, but there's a non-linearity in the laws of the universe. Now, people will tell you the electromagnetic field is not linear, and they have to be wrong, because what happens when you open your eyes? You see things. You see light. That means the light interacted with your eye. And your eye is made of particles, which are standing waves of electromagnetism. So it does interact with itself, which, according to the physics, that interacting with yourself is the same as being nonlinear. They're exactly equivalent. So when we say that light is non-linear. They're going to argue, but they're wrong, because they're only measuring very, very dim light. When you get the light from a star, it's extremely dim. If the nearest star is over 4 light years away, and one quantum of emission happened, that's now spread over a sphere with a radius of over 4 light years. How much of it do you think went in your eye? Not very much, a tiny, tiny amount. So what's the chance that it will get detected? It's not very good, but in fact it can happen, and a proportion of them it does happen, and so you do see things. Now that's proof that it's non-linear, and to defy anyone to show otherwise. So that's one of the little obstacles that they have in modern physics, is they think that light is linear. It's a linear in an approximation. When it's very weak, it's extremely close to linear. You can't tell the difference, but when it gets focused in your eye, you can. So that's very important. So let's go back to the universe with this one very big standing wave, and it's non-linear. The thing about a non-linear wave is it develops harmonics. This is standard physics. It's not something I made up, but in standard physics, a wave makes harmonics. And that's the end of it. If you pluck a guitar or anything, you get the original wave, but you get these other waves that are harmonics of the original. And that's standard physics as well. It's very commonly known for musical instruments and so on. But I'm going to tell you one more thing. In the harmonics theory, each of those waves then does the same. So the reason for that is, as the energy gets leaked from the fundamental wave to the other ones, gradually they build up in strength until they are strong enough to be also considered nonlinear, and at that point they begin to develop harmonics as well. Well, they're doing it all the time, but it becomes significant. And when you do that, you get this cascading effect that the fundamental makes harmonics of itself. Each of those then does the same, and you get a very particular pattern of waves. So that particular pattern, I'll show you some diagrams for it. So you can see that if we start with frequency 1, it develops its harmonics, which are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. And each of these does the same. So frequency 2 develops frequencies 4, 6, 8, 10, 12, 14, 16, etc. And frequency 3 makes 6, 9, 12, 15, and so on. Frequency 4 makes 8, 12, 16, and so on. 5 makes 10, 6 makes 12, and so on. And you may have noticed that the number 12 popped up a lot of times. In fact, the frequency 12 can be made, there are 8 different paths to get to it from the fundamental frequency. And that means with those 8 paths, each is contributing some energy. And so the 12th harmonic is 8 times stronger than the 11th or 13th harmonics. And that's why 12 is very important. In many systems, the ancients knew 12 was important, and 12 is very important when we come to harmonics. If there's a strong wave, there tend to be other strong waves at double or half the frequency, at 3 times or third the frequency, at 2/3, at 3 over 2, and so on, 4 over 3, and so on. And at a 12 times, it is, and 1/12 of it, there tend to be other strong harmonics linked to it. So we can add up the columns in this, and we can get how many ways each different harmonic is made. And when we do that, we start to see a pattern. When we move on to some larger numbers, which we can do by hand, we can do the numbers up to 100 by hand easy enough, we find that there are certain numbers like 48, 60, 72, 96. And these ones are in the proportion 4, 5, 6, 8 times 12. When I first started looking at cycles, I found exactly those ratios in very strong cycles in the New Zealand economy. When I came to the Cycles Foundation, I found that Dewey had a bunch of cycles related in proportions of 2 and 3. So he had divided by 2, divided by 4, divided by 8, also divided by 3, 9, also by 6, 12, and so on. And all of these ratios that I'm mentioning there pop up in Dewey's table as well. So, and he wasn't the only one. There were other people also that found this pattern of strong cycles in many, many things. So this prediction that's being made here by the nonlinear nature of electromagnetic waves is giving us the correct answers for the relationship between different cycle frequencies. When we go to still higher numbers, we find that there's more and more that have these musical relationships. Music, it really is the music of the spheres, pervading the whole universe. I'm covering a lot of ground. I hope it's not too heavy or too complicated. I just mentioned now, I'm sending this video in to be shown at the conference. I originally was planning to come to the conference. I paid my conference fee, and I was about to book my airfares when a number of things happened. One of them was that I read an article that said that Trump had given an order. They made an AI to search all the social media for people that were pro-Palestine, anti-Zionist or anti-Trump. At that stage I decided, because I'm in all of those categories, that they're not going to like me because I post stuff like that all the time. Shortly after that, I let Richard know that I wasn't going to come, and he was a bit disappointed and hoped to get me to revise that. The following day, a Frenchman got stopped at New York, which is where I was going to come, and he got sent. They took his phone and they searched it all, found that he was anti-Trump, said things that criticised Trump, and he got sent away. Many countries are giving advisories not to travel to America. I'm taking that advice and not coming, but I'm recording my talk here so that you will know what I wanted to say. I also want to apologise for not being here when I was advertised as being in the program, and I was the one. I asked Richard to have a science day ahead of the 2 days of markets, and he thought that's a very good idea because Dewey himself was very keen. He encouraged both the scientific side and the market side, and in my experience, the Cycles Foundation has been most effective when it's done both of these things. And so we need more science people. I'm encouraging more scientific people, when they find cycles, to report them to the Cycles Foundation and to join it and to learn about stuff. Dewey did some wonderful discoveries back in time, and he made very good statements. Another person did that was Chizevsky in Russia. Now, America shouldn't be fighting with Russia. Both of them have done good science, and they should be talking to each other about that. They did a space program together. That stopped, and there's a lot of stuff. So that's a little interlude to try and encourage people to look at these other issues. I don't think scientists should be allowed to ignore the problems of the world, like in Palestine, like in Ukraine and so on. These things have to be addressed by rational people. We've got too many irrational people running governments, too many opportunists, and so on. So we need rational people to look at these things and speak out. You've got to speak out. You've got to be prepared to get into trouble. Okay. So let's do some more of this harmonics calculations based on the fact that the universe has standing waves, and that they develop harmonics, and that energy flows from long waves to shorter waves, and from them to shorter still and all the way down. When we do that, there's this graph that shows the calculations. When I first did this, I did it up to 1 million. Then I wrote a cleverer program to do it up to 10 to the power of about 20. And then each time a new model of faster processes came out, I did it a bit further, 10 to the 30, 10 to the 40, 10 to the 50. I haven't bothered to do it since then, but you could do. It can be calculated further, but that's enough for all practical purposes. When we do that, we discover that there's a thing I call the main line of harmonics. In each range, I pick out the strongest waves, and I look for ones that are at prime ratios. So the strongest waves to start with are 1, 2, 4, 12, and we go 1 times 2 times 2 times 3. These are the things that Dewey said, ratios of 2 and 3. From 12 we go to 24, 48, 144, 288, more ratios of 2 and 3. But eventually we hit a ratio of 5, and later on a 7, and later on other prime numbers. So that's important, and Dewey only showed the 2 and 3, but if you look at his table of cycles, you find that he's got 1.11 years, 2.22 years, 4.44. He's also got 11.1, 22.2. These are the solar cycles, and they're related by a ratio of 5 or 10, if you like, which is a 2 times 5, to the cycles he observed. He also had some cycles that didn't fit. So, for example, the 40-month cycle, he determined it very accurately as 40.68 months, which is 3.39 years. Now, that does not fit in his table of the cycles. However, if you multiply it by 7, multiplying it by 7, you get about 23.7 years, which happens to be double 11.85 years, which he also didn't have, and a third of 71, which he did. And those other numbers link in to his main table. So by taking the main table and dividing by 7, you get another whole set of cycles, and many of those have been observed in solar phenomenon. Right from one of the most common ones they call a 155-day cycle is sometimes reported as value slightly either side of that. I think it's 154.7 days, and they've found other cycles that are half of that, a third of that, a sixth of that, and so on. And those cycles are in many phenomena in the sun. Later on, I discovered that in fact the 155-day cycle is also present in the monsoon rains in India. Now, it's not obviously present because the monsoons have a very, very strong annual cycle, and if you remove the annual cycle properly and then analyse it, it turns out to have this whole series of related by 2 and 3 cycles in it as well, which are all at 1/7 of the cycles Dewey. So there is clearly a ratio of 7 there and a ratio of 5 above that. These things are predicted by the calculation of harmonics that will have lots of ratios of 2, slightly less of 3, occasionally a 5 and a 7, and eventually 11, a 13, and 17, 19, and so on. And those ones are not at all obvious to start with. You have to collect a lot of cycles from very long to very short to detect them. So when we start doing that, when I went to Crimea in 1996 and I gave a talk about harmonics theory, a very sturdy looking Russian man, S.N. Afanasiev, came up to me and shook my hand vigorously and poked a book in my other hand, and I took it off him and opened it, and it was all in Russian, and I don't understand Russian, and he doesn't speak English, but I flicked through the book and I saw some tables and I gave him a thumbs up, and it was clear to me he was telling me he's observed a lot of these cycles. One of the ones he observed, which the Western geologist said is about 600 million years, he says it's 586.2385 million years. So he'd worked out all these decimal places of it, and he's done a lot of work with a method he calls nanocycles method, and they originally found it from the salt mines. They found these layers in the salt. It's also found in the varves on geological deposits, and so you get many cycles there, and at the current time you get a strong 18.6 or 9.3 year cycle in many things. And many people have reported this. Louis Armstrong at the Cycles Foundation used to report that in agricultural things, and it's in other things as well. It's due to the motions of the moon's orbit. It wobbles about the Earth's axis, and at times it's tilted strongly to the Earth's orbital plane, at other times less. And that variation causes, because the moon causes tides, we know it of course does the tides, strongest component of the tides in the sea. It also does tides in the atmosphere, and combined with the sun we get these tides, and that affects the rainfall. Now, because rainfall often happens at particular times of the year in many places, you have to look at how does that interact with the year, and he does that, and he shows like the 9.3 cycle. You're 0.3 of the way after one cycle, you're 0.3 of the way through the year. After 2.6, after 3.9, you're nearly back to the same place. So after 3 of those cycles, which is nearly 28 years, you're almost back to the same place. And in actual fact, you come back to the same place on average every 31 years. You can get that answer by dividing 0.3 into 9.3. And he shows these, and he shows at any one time what this pattern of these cycles are. If you go back, he then shows what it was fractions of a million years ago, and he goes back in those steps, because the moon's orbit is gradually changing over time, and so this pattern of cycles gradually changes. And when you go back a long way, it gets very different. Another geologist, George Williams in Australia, found some very interesting cycles in a thing called Elatina formations. And they had an about 12-year cycle, but there was also, from memory, a 156-year cycle as well. But the 12-year wasn't exactly 12, it was 12.04 about. And when you divide the 0.04 into the 12, you get about 300. There was a cycle of that, but the particularly strong one was 150-something years. And that, using that information, I could calculate extremely accurately when that, he gives a date of about 600 and something million years ago. Using Afanasiev's data, I could calculate extremely accurately when those formations were made, to a fraction of a million years. So when we start to embrace cycles fully and understand how they happen, we can find out a lot more stuff about the universe. That cycle of Afanasiev, 586 million years, when I worked upwards in ratios of 2 and 3 and 1 of 5 and so on, I found other cycles. There's a 2,300 to 4,600 year cycle, which have been reported by climatologists and understood as being related to planetary alignments in the solar system at those intervals. But you can go to longer still ones, and you get cycles of 1.11 million years, and also 26.7 billion years, which is a cycle of mass extinctions. Now, that one is still related by ratios up to Afanasiev's 586 billion year cycle. In fact, if we take his cycle and we take exact ratios from it all the way down until we get to the known periods in the range of Dewey's ones, one of the cycles we get is 11.8622 years. That's the exact figure we get from Afanasiev's one, and that is also the exact period of Jupiter around the Sun. I always, even before knowing about this, I had considered Jupiter's period as the place to base the other ones off, with the ratios of 2 and 3. So 3 times that gave 11.5 something year, 11.58 years, which was very close to what I found for my cycle. And when you halve it, you get very close to Dewey's 17.75 years cycle as well. So they all fit together exactly over a very long range, and we can then, in that interval up the top part, we discover there's a ratio of 11 between the 26.7 million year and the longer ones. There's also a ratio of 13 between the 4,600 and the 2,300 year cycles and some of the shorter ones. Now, those ratios of 11 and 13 are very important, because the harmonics theory predicts a sequence of how this all happens, and they aren't expected to happen early in the sequence. They're expected to be a long way down. So what I did is I took the prediction of the harmonics theory, the relative periods of all the cycles that come out, and I compared them to all the known cycles that we have, and I moved them relative to each other on a log scale, just gradually, a fraction of a percent at a time, to see where did they match up. And it gives slightly better fit, slightly worse, slightly better, slightly worse, slightly better, slightly worse. And then suddenly it gets to a place where it gets some fantastically good fits. And the very best one is a period of 1.4 times 10 to the 23 years. That's 10 million times longer than the age of the universe, according to the Big Bang. So what I'm saying is the Big Bang is totally wrong. There's some other reasons I can say that as well. But the longest cycle is that long. Incidentally, around in the 1990s, I began to do a thing called Vipassana meditation, which is the teaching of the Buddha. He wasn't trying to start a religion. He was trying to teach people how to come out of suffering. And it starts with the observation of the breath here, and we observe the sensations through the body. One of his pupils asked him one time about how long does the physical universe last? And he said, well, it arises and passes away on a very long cycle. And he said, how long is that? And they didn't have base 10 notation then, so the way he described it was, using the units of the day, a hole that's 7 miles by 7 miles by 7 miles, if you fill it with sesame seeds, and then you take one out every 100 years, when you get to the end, that's how long the longest cycle is. And so I said, okay, sesame seed looks like about 1 millimetre to me. So I assumed a sesame seed is 1 millimetre each way, and I divided into the 7 miles each way, converted into kilometres and things, and the answer I got was 1.4 times 10 to the 23 years. So I'm not the first person to get that answer. I may actually only be the third. There was also, in the days, at one stage, one theory said that protons might decay. And if they did, they calculated the lifetime and they gave an answer, and it's very similar to that answer. I can't find that exact equation. If anyone's got that, I'd like to know that equation to see how it fits into the physics constants. So, yeah, there you go. Let's go back to the wave structure of matter again, and what's actually going on in terms of the ether. A particle has shells around it that are oscillating opposite ways to each other. Sometimes in quantum mechanics they describe particles as having something like these opposite charge things going out, and this is what I'm describing. So far from the particle there are the layers moving back and forwards like this, one after the other, going outwards and getting weaker as the inverse square as it goes out. Near the middle, and more complicated things happen, but we're not very much concerned with near the middle at this stage. For the electron, it's understood what happens there. For protons and neutrons, we don't know exactly what that does. If people will start to look seriously at the wave structure of matter, they will be able to determine what's happening with protons and neutrons. When they do that, they can start abandoning all these extra dimensions and all the other things that they've got in their equations at the moment, and do regular three-dimensional space and time. So taking these particles, protons and neutrons make up the vast majority of the mass of the observable universe in terms of matter. So as we move outwards from them, we get these shells going like this. If you've got a massive body like the sun, when you're far from the sun, the direction of the waves is all very similar because the sun's quite small compared to a distance that we're at. So all of these things are combining to make these layers moving like this. Now, what effect does that have? It's the ether that's doing a little wobble there. The light that's travelling through the ether is getting affected by that. So light that was trying to travel like this is going to go a little bit of a wobble like that, or if it's going this way, it's going to go a little faster and a little slower. Only a very little bit. The actual motion of the ether due to the particle is incredibly small, extremely, extremely small. So when we do these calculations, we know that there is such a thing as a black hole. So the question is, at what point, well, no, let's get the formula first. When light is traveling radial relative to a massive object directly towards the object, then it's doing this little wobble as it comes in. The equation for that is when you're going one way, it's this the hypotenuse of this angle is representing the speed of light, and this way here is the velocity of the ether. It's extremely small, as I said, unless you get very near a black hole where there's a very lot of mass, that starts to become significant. And the equation has in it that the square root of c squared minus v squared for the actual effective forward motion. When you're going the other way, transverse to the matter, then it gets sometimes assisted a bit in the motion, sometimes slowed down. So you get C plus V and C minus V alternating, and the net result of that is you get a C squared minus V squared effect. So in one case it's got a square root, in the other case it hasn't. These are exactly the relationships that you find in relativity between the two directions. I should mention a fellow, a Russian named Ivanov, who also did work on understanding the wave structure of matter. There's a website of his still in existence, and it has a lot of diagrams showing what's going on. And he says, of course, that in actual fact, there's a shrinkage in both directions. According to relativity, there is this effect, and it's twice as much in one direction as the other, more or less twice as much. So when we get nearer to a black hole, light that's travelling towards a black hole, it starts off travelling straight and it gets a little wobble, and as it gets nearer and nearer it gets a bigger wobble, and the more the wobble it gets, the less forward it's getting. It's going side to side at the speed of light instead of making any progress. And so the light never actually gets to the event horizon. It gets slowed down as it gets there. This whole time thing and all of that, the equations of relativity are correct. The explanation that space is distorted is not correct. The true explanation is that the ether is wobbling, and that has an effect on the progress of waves. And so when we do that, we can get all the equations of relativity correctly from this understanding of the wave structure of matter. As far as I know, no one has attempted to do that before, but people have understood what's happening in the ether, and they've understood the wave structure of matter, but no one's put it together to say this is actually an explanation for what happens in relativity. When we do this, we find that in actual fact we can use Euclidean space in absolute time and get the correct answers, because these things that Einstein did, when how the observer sees it, he's quite correct. He didn't make any mistakes on all of that, but the explanation behind this is what's going on with the wobbles of the ether. And when we do that, we don't need any of these extra dimensions. We don't need space that's warped. We just need to understand that the effective velocity of waves in the ether is different than what we expected it to be because of the motions the other way, or because of the motions in that way. But it's the motions of the ether that cause the difference. So this takes us back more, 100 and something years to what was understood. And if we use the ether from that, and we use Newton's understanding of how space and time were, and we do the correct calculations, we can get the answers, all the answers that modern quantum mechanics get, all the answers that general relativity gets. The equations of those things are quite good. They do explain things, but the understanding of what's going on is incorrect, and they end up with excessively complicated interpretations. So what I'm saying is you can do both quantum mechanics and relativity with much simpler understanding. When that understanding is there, I believe it will lead people to work out the exact nature of the waves of protons and neutrons, and we end up with a new physics that's very simple compared to the existing one in terms of those things. If we consider these waves now, this cascading effect from the very largest wave in the universe down through the scale of galaxies, stars, planets, moons, and so on. There are waves that determine the distance of all of these things, down to cells, atoms, subatomic particles, nucleons, and then eventually quarks or quarks, whatever you want to call them. So at the larger scale, there's huge energy in these waves, and they're extremely slow. So let's consider that energy in those. The straight harmonics theory doesn't say the relationship of the harmonics. Is it 1 upon f or 1 upon f squared or so on, the energy? It works in any of those cases. So the most logical thing seems to be that it's 1 upon f squared. This is a common thing. So if I make that assumption, which I did in the early 1990s, and do the calculation, it turns out at that stage it explained quite well the missing mass problem, which was the fact that there seemed to be more matter in galaxies at the outer edges than there ought to be from adding up all the visible things. As they've done this for clusters and so on, they've got some sort of an idea of how the missing mass goes by scale. They don't call it missing mass anymore. They've changed the name to dark matter and dark energy and things. But the harmonics theory will give an explanation to all of this quite naturally. It says that there must be this energy at these large scales. They are trying to define it as particles. It's not particles. It's waves. It's extremely large waves, and you can't detect them anyway. There's no way to detect such large EM waves unless you make a detector that's bigger than a galaxy. So that's not going to happen. So all these very large scale waves, all the smaller waves in them, and as that one wobbles, the little waves that are sitting on it, they're carried along with it in whatever happens. And so they're affected by it, particularly if they're harmonically related to each other. They will have an effect on them. So we get waves, some of the long ones, like the 586 million year geological cycle, you can detect that in two ways. One way is when we look out and see all the galaxy clusters, there are groups of galaxies at regular intervals. Because they didn't know the Hubble scale, they expressed that a weird way. But once you know what this Hubble constant is, you can determine what is the spacing between these. And when I averaged some years ago the last 10 values of the Hubble constant, it will give that cycle as 500. That spacing is 586 million light years. In other words, it's the same as the geological cycle of 586 million years. So we've got a connection between those two things. And in fact, at that stage, long before they worked out what the Hubble scale was, I was able to predict the Hubble constant very accurately based on the spacing of these galaxy clusters and Arsenovius cycle in geology. The two of those together gave me a value of the Hubble constant of, I think it was 71.2, and when I averaged the last 10 values that were published, they gave a very similar value within 0.1 of that. So this method can get the scale of the universe far more accurately than other methods, because it hasn't got all the distance ladder and all of these other complications going on. As we come down to smaller scales, there are some waves at 26.7 million years, and that one shows up as mass extinctions. So every 26.7 million years, more species go extinct than they do at the times in between. Don't worry, there's not one coming up soon. We are having a mass extinction, but it's not caused by that, it's caused by human activity and the stupid things we do, wiping out things. That's another whole story, but give attention to it. It's not caused by climate change, it's caused by the destruction of the habitats of animals. And if we wipe out all the insects, we're not going to be any crops, so we're all going to die. So we need to give attention to those things. Just a little sidetrack there. So this 26.7 million years, there's also a 36.7 million year one, which is one of the simpler harmonics of the 586 million year cycle. Those two interact, and every time when three of one happens or four of the other, they come together and you get an extra big mass extinction, and that shows up very clearly in the mass extinction record. So we come on down some more. We come to a 1.11 million year cycle. Now that's an interesting one, because the outer planets, particularly Jupiter and Neptune, have an exchange of energy in their orbits over that period, and so you get that showing up in a lot of different things, and it also shows up in the reversals of the Earth's magnetic field. They say that it's not cyclical, and it's not entirely cyclical, but there are cycles in it. There's two particular ones, one of 1.11 million years and one that's probably 8 times that. It's around 9 million years. And they show up throughout the record. And there are other shorter and other in-between cycles as well. That can all be explained, I think, from another study I did, which is about how the planets affect the inner part of the sun and the heat coming out. Coming down to shorter cycles, there are there's a couple of climate cycles of 4,600 years and 2,300 years. Those ones come in the sequence of strong harmonics as we come down. I think I mentioned the main line of harmonics. So the main line of harmonics, a lot of these ones I'm mentioning are in the main line of harmonics that are connected by ratios of 2 and 3 to each other, and occasionally a 5, and very occasionally 11, 13, 7, 17, 19, etc. Then we get into the range of cycles that are the ones that Dewey reported, from hundreds of years down to weeks and so on. And we have lots of records of cycles there. One of the interesting things about when we match up the known cycles, which I'd put in, against the pattern predicted by harmonics theory and determined what is the fundamental cycle of the universe, I'd put in a lot of known cycles, but there were several I didn't put in. One of the ones I didn't put in was the 9.6-year Canadian lynx cycle. This came out and said there should be a cycle of 9.638 years. Now, the cycles, the 9.6-year cycles reported by Dewey, there is about an equal number of 9.6 and 9 2/3 years, so 9.666. So averaging those, we get 9.633. Certainly not accurate to the last digit, but around 9.63. So we get a very good agreement between what harmonics theory predicts and what we've actually observed happening. A cycle that appeared to not be related to the other ones, but in fact is. But you haven't got the last ratio of 13 done. It's got that one. It's a leftover from the previous set. So it also gives the 40-month cycle. Originally, I got 40.67 months for that, and I told that to one day I told Richard Mogi I get 40.67 months, all the different directors of the Foundation for the Study of Cycles had been getting 40.68 months for quite a few years, and we agreed that was a pretty good fit. But one day, Richard Mogi got in touch with me and he said, "Ray, we've got new data, and the analysis for the whole period now says it's 40.67 months." So that was quite a funny one. So we can get good agreement between the theory and the observations for cycles. I'll put some graphs up now showing a number of the predicted cycles from harmonics theory, and some marks on them that show the observed cycles from various different disciplines, and pretty nearly all of the commonly observed cycles do match to the predicted ones by the harmonics theory. So we can say it seems to work. I think I should mention any problems here. With the calculations that I do for the harmonics, where I just assume that every path is exactly equal, that's probably not exactly true. It's probably very, very nearly true, otherwise the results wouldn't have been this good. But I find that when I get down to the period of weeks, the cycles work to there, but there are commonly observed cycles in the range of minutes and seconds and so on. I know what the commonly observed ones are, but the linkage between the longer ones and those ones is not clear. I can't say what the ratios are, and it doesn't follow the pattern that I get from my harmonics calculations. So there's a problem. I think that it's the nature of the standing waves, that the equation isn't that it does it exactly as I've assumed, and I never really thought that it would. So it involves finding the Taylor expansion of the waves, and working from that. And I think it will be possible to get corrections to that and to go down to smaller time periods. The pattern is still there. There's still lots of 2s and 3s, and they've odd 5 and 7, and even the other ratios. And when we get to the atomic realm, when I did analysis, not assuming any knowledge of those ratios, but using just looking for, it's what I call Kotov's method. Kotov is a Russian astronomer, and he did a lot of work on the 160-minute period, and he had a method which he called communality, and so he would put in, like, for example, binary stars or asteroids or something's rotation periods. He'd put those large numbers in them and look for values that fitted in ratios to those, not my harmonics theory ratios, but any ratios. And he found, for example, a very strong 160-minute cycle in those things. And there's a known 160-minute cycle in the sun. And all the black holes that we observed show strong relationships to 160-minute cycles as well. So using his method, I put in the masses of all the known, of all the commonly observed subatomic particles. I haven't used some of the more esoteric ones that have been discovered since then. It doesn't matter. The thing that comes out is that there is a pattern in them, lots of ratios of 2 and 3 as expected, and there are ratios of 17, 19 and 23 occurring in that order as we go from the lightest to the heaviest. Now, why does this work for masses? I thought these were time periods. Yes, they are. Mass and frequency are the same thing. As a Nobel Prize said, when I said, there's 3 things we can talk about: mass, energy and frequency. He said they're related because E equals h nu. Nu is frequency. That relates energy to frequency. And there's E equals mc squared. That relates energy to mass. So those equations say that mass, frequency and energy are all measures of the same thing. And he said, what's the most fundamental? I suppose frequency is. Yes, frequency is the most fundamental. That's the oscillations. The whole universe, everything in the universe that we can detect are nothing but oscillations. And at the atomic realm, the pattern of those oscillations is exactly what's expected. It's consistent with the harmonics theory in the common ratios. And the pattern of the primes coming in the correct order, 17, 19 and 23. That's not exactly where I expected them to come in, but they are expected to be in that order. So there are some problems to be resolved there to extend the theory to make it more clear and more exact over those longer intervals. So, yeah. I'm not going to do all the details of cycles that are found in the many things that I've mentioned a few of them. But for the rest of those, I would recommend you to watch the series of interviews that Richard did with me about harmonics theory. There are 8 videos, numbered 1 to 8, part 1 through to part 8. The stuff is taken a bit slower in there because Richard wanted to make sure it was all very clear. So he'd pause me and say, hang on, let's get this clarified and so on. And that's very good. That's not happening in this one, so I'm racing through it all, and you're all going to be left with your head spinning. Sorry about that, but I'm trying to get it to fit into about an hour. So I'll put up here a QR code which will take you to a page which will have links to all these other things, like Richard's interviews of me, some other interviews other people have done of me, and various other useful material that you can look at. A lot of graphics and other things, and that'll be hopefully a useful resource for people who want to look further into these things. I want to say a special thanks to Richard Smith and all the board members for how they're conducting the Foundation for the Study of Cycles now. I'm on the board, but I'm retiring now because I'm the science director, but I'm getting too old and I can't really contribute like I used to. So I want to encourage them to keep on going, and it's especially important to encourage to get more scientists into this area. There's going to be an announcement about, I have a trust called Radiance Trust, which is a charitable trust, and one of the things it does is support cycles. It's particularly interested in advancing harmonics theory, so those things will be given the most priority. Second most is other cycles analysis that leads towards being able to analyze those patterns, and thirdly towards the demystification of physics. And so those are the areas which, if people are wanting to do those things or have done those things, they can be put forward to be considered for grants under those things or awards. So that's something else that will be discussed at some point at this conference. Thank you for having me, and thank you for all the assistance of everyone in getting this to happen.